All right, cool. So the big things that we've done so far, just to recap, so geometric series. If that ratio on the inside of the geometric, if that's bigger than 1, it's going to diverge, right? If it's less than 1, it's going to converge. I think we're kind of okay with that concept, right? I hope. Okay. So that's one series that we know how it converges. The P series, the one we just did, the P series, if the denominator, if that power is what was the rule? If that power was bigger than 1, right, then it's going to converge, okay? It's going to converge. So it's kind of backwards a little bit of the geometric, but if it's bigger than 1, it converges. If it's less than 1 or equals 1, then it's going to diverge, okay? So those are kind of the general ones we have so far. Plus we have telescoping, I don't know how you say that word. I think telescoping. I'm just going to stick with telescoping. What's up?
I never went over what happens if it's negative.
It can't be for a P series where you just, it doesn't fit in the little.
Technically just goes up.
Technically just goes up, and it's not really. It's still a P series, but if it's n to the 5th power, that's going to diverge because of the a sub n divergence test thing. So you know what I mean? Like if the term doesn't go to 0, right? If the term goes to 3 or 4, something like that, it's got to diverge, right? So that would fail just by that. So the P series strictly is usually between. It's usually positive. So. Anyways, all right. So that's all the stuff that we know that we hopefully have a rough idea for today. So if I took a look at this series right here, and I want to just basically find out if it's converging or diverging, and I can actually maybe find out where this one's actually converging to. On some, I actually can find it, like the telescoping sequences and the geometrics. We have little tricks and ways to find out exactly what number it actually goes to. Sometimes we don't know quite yet. We're just saying, is it converge or diverge? Another strategy we have is the integral test, and we just did that. Hopefully we're kind of okay with that. Anyways, if I look at this one's geometric, even though it kind of doesn't look like it, but it's geometric. You can write that as a 1/3 to the n power, so that's geometric. And so that guy right there is going to converge. Okay, so it's converged, and the reason it converges is because that number right there is less than 1. We've done that before, not a big deal. Okay, now let's say I have a series like this, n equals 1 to infinity, and let's say we do 1/2 plus 3. Now, that itself is not a geometric sequence. We're not going to be, if you were to write out the terms right there, you're not going to be multiplying by the same thing every time to get from one to the other. However, it looks like it's really close to a geometric series, right? You'd probably look at that and say, oh man, if I just lost that 2 right there, if I can just erase one of those numbers from my mind and say, oh yeah, that's geometric right there, okay? So what we want to do is what's called the comparison test. So we're going to take a look at this guy, and we're going to try to compare it to a different series, or a different a sub n term, okay? So we're going to try to compare 2 series. So we're going to take whatever our a sub n term is, and we want to create a new one. We want to create whatever b sub n is. B sub n will be our new terminology that we're going to be looking at. So our a sub n, that's what we start with. We're going to have 1/2 plus 3 to the n. And I want to try to compare that to something that I think is close, that I know the answer to already. Okay? So for this guy, I would compare that to 1/3 to the n. And the general idea here is this. If I can compare these 2 series, and let's say I have this series. Does this series converge or diverge? We should know the answer. It converges, right? So if this guy converges, right, and I have a series that's smaller than it, won't that have to converge? Does that make sense? I know. Okay. If all the values are less than that, if all the values are less than a converging sequence, then that guy is going to have to converge no matter what. Okay. The other way to look at that is if I pick a new one right here, let's say I pick a new one, and this diverges, and this one's bigger than it, well, if it's bigger than one that's diverging, it's going to be divergent. Okay. So that's kind of the logic with the comparison test that we're looking at. If we have one and we find out it's diverging, and we find one that's bigger, that's got to diverge, okay? If we have one that's converging and we find one that's smaller, it's got to converge as well, okay? So that's the general idea of the comparison. Yeah.
So if it's not the other
if it's not the other way, it doesn't work, okay. Right? And we'll take a look at that. So if I have a sequence that converges and then I find something that's bigger than it, it doesn't really tell me anything, right? Not necessarily anything, okay? So it's got to strictly be on one side or the other, okay? So what you do is you pick a sequence that you think you know the answer to. Like you guys know the answer to this. You guys know that this guy converges, right? You guys okay with that? So this one converges. So I want to compare this one with the one that they gave me, and I just want to see which one's bigger, okay? And I'm looking for which one's bigger for every term all the way throughout the sequence, okay? Well, if you think about it, these are pretty much exactly the same. The only difference is this denominator is 2 bigger every single time, right? So this denominator is going to be bigger, right? Is everybody okay with that? So 1 over a bigger number means a smaller number. So this is actually smaller. So I would put a big old inequality like this. This guy is always going to be smaller than this one, no matter what. Okay? So if this one converges, this one has to converge. Okay? So by the comparison test, I would say that this series right here converges. Okay, and I'm not really looking at what it converges to. I don't care too much about that yet. I just want to see if it converges or diverges. Yeah, what's up?
So if one of the functions is greater and it converges, then the smaller one has to converge.
You have to know the bigger one though.
Right.
Right. Right. But if you know, let's say you know the smaller one and it diverges, then the bigger one has to diverge as well. Okay? So it only works in those two directions. And I'll show you an example where it doesn't work, where people will just try and it'll backfire.
So if the smaller one converges, then the bigger one.
Then we don't know. It could be just barely above it and might be fine. Okay? So we just don't know, unfortunately. But that just means we might pick something else for our comparison. Or we do a different test, one of the two. Okay. The other tests still have to work. Like you can still do like the divergence test. You can still find out if that term goes to 0. If that term doesn't go to 0, then it's going to have to diverge. So sometimes that might be a fast way to do it. This one does go to 0, so it doesn't really tell us anything, but it's worth a shot. Okay. So anyways, that's the basic premise of the comparison test. Just the basic comparison test. Okay. Let's take a look at another one.
There's a lot of logic and all
A lot of
that.
logic and not a lot of math. A lot of logic, not a lot of math. Let's do this series. Let's go ahead and say we're going n equals 1 to infinity, and we'll do 1 over 2 plus the square root of n. And we're going to use the comparison test on this one. There's basically two kinds of comparison tests that we'll do. First one we're doing is called direct comparison. Pick one and you compare it to the other. Directly. There's no extra stuff to do. We have one other to do today too, but first one's direct comparison. So comparison test for this guy, you probably pick one that you think is close to that, right? So what would you guys probably pick? 1 over square root of n would be a good idea, right? So we have 1 and then over 2 plus the square root of n. And I'm probably going to try to compare this to 1 over the square root of n. And I just want to see which one's bigger. Okay, so which one's bigger? The one I picked, right? This one's bigger, right? The denominator on this one is bigger than this one. So if the denominator is bigger, then the number is smaller. Okay, the entire series will be smaller. So my sign's got to go this way, right? Everybody okay with that? Okay, that one's bigger all the time. Okay, now I want to check, is this guy converge or diverge? Right? This power series that diverges, right? This is 1 over n to the 1/2 power. Remember, if that power is less than or equal to 1, then it diverges. So this one diverges. Okay? So I've got a series that diverges, and I've got something that's smaller than it. Does that tell me anything? No conclusion on this one. Okay? All that means for the no conclusion is that you picked a bad thing. Or you can't use the comparison test, one of the two. That means you want to pick something else other than this guy right here. Okay? So let's pick something else. Maybe. What else could we maybe pick? I don't know. Let's see. 1 over 2 plus the square root of n.
The root.
1 over 2 is not really a series, though, right? And that's not always going to be the same as the other one. Let's say we picked 1 over n. Now we know by the power series, 1 over n diverges. Right? That was that weird one that diverges to the first power. And now I want to see which one of these guys is bigger. Which denominator would be smaller? Probably this one, right? This denominator is going to be smaller, right? So if I plug in 100 for n, this one's going to be 1 over 100. This one's going to be 1 over the square root of 100 pretty much, right? So this one's going to be a smaller denominator, which means this number is going to be bigger. So this sign is going to be going this way, okay? So this one's going to diverge, okay? This one's going to diverge because this one diverges, so anything bigger than that is going to have to diverge, okay?
Isn't that just comparing 1 over infinity to 1 over infinity, though?
Kind of, but it's almost like a L'Hopital's rule, like are the infinities the same, or if we're calling this 1 over infinity something and this is a bigger infinity for sure, then it might draw closer to that. Or we've done like infinity multiplied by 0, which is really infinity divided by infinity. Those might be different levels of infinity, so it's not like they're always going to cancel out or anything like that. But we know for certain case that this infinity is always going to be bigger than this infinity, right? So if this infinity is a diverging infinity, if you want to call it that, this one's got to be bigger than it. So that's obviously going to keep on there. What's up?
I don't see how that one's bigger.
How this one's bigger? Or I'm sorry, how this one's bigger? If you were to plug in, let's say you were to plug in 100, right? This one right here would be 1 over 100, right? Which is pretty small. This one, if you plug in 100, you're taking the square root of 100, so this would be 1 over 12. right? So this one's always going to be bigger. Now, the way to look at this, I know it's kind of backwards thinking a little bit, but you really look at the denominators here, and you see which denominator is smaller. And whatever the smaller the denominator is, the bigger that number will be. So this one is going to have a smaller denominator for all n's, right? This one's going to have a bigger one. So that's my comparison test between those two. Right. All right, let's do one more. And you might be able to do some of these guys in different. Oh, not the integral. What are you doing? Sorry. Okay, we'll test this one in a couple different ways, maybe. Checking out if this converges or diverges. You could do the integral test on this one. Nothing wrong with that. Nothing wrong with doing the integral test. I would even probably go a step over that, but we'll find out. Maybe. Yeah, what's up?
Can you use P-series?
Can you use P-series? You can, yeah, you can use P-series. Sure. Let's compare that to a P-series. That's fine. So what do you want to compare it to? That's what you probably should do on this one. P-series is like 1 over n to a power, right?
Yeah.
Okay. So let's just do 1 over n. Why not? Okay. 1 over n is kind of a good comparison. You'll probably use that one a fair amount. Okay. So let's compare it with 1 over n. We know 1 over n diverges. Right? So we want to take the look at the natural log of n over n. We want to see which one's bigger. Hopefully, if this one's bigger, then it will diverge. If it's smaller, then we don't know. Then we don't know. Maybe we need to pick a different thing here. Okay? So we have to figure out if this one's bigger or not. Okay? Now, as I plug in bigger values of n, think about this. Bigger values of n, the denominators are really going to be a push. They're going to be the same, right? So if I look at the top on this one's always 1. If I plug in 1,000, the natural log of 1,000 is going to be bigger than 1, right? And so this guy's got to be bigger. So I would say this guy's going to be bigger, and this guy is going to diverge. Okay? Now, a couple tests that you can run. We know this one diverges. We could also take this term right here and we can do the integral test on that. That's one option, right? You'd have to do a u substitution, probably make u the natural log of n, right? I think we've actually maybe even done that problem before in that section. You could also maybe check the a sub n term. I don't know if this one backfires, but that's a good thing to check as well. See if as that term goes to infinity, does it go to 0? If it doesn't go to 0, then it's got to diverge as well. Okay, which I don't know if that does. That's 1 over n, big number, so it does go to 0. So, anyways, what's up?
So you could do L'Hopital's rule 2, but that doesn't give you like a for sure answer.
L'Hopital, right. L'Hopital's rule is good to use if you want to check for divergence, right? It'll guarantee a divergence if you get a number other than 0. So if you do L'Hopital's rule there and you get like 2, diverge on that. All the L'Hopital's rule is for is basically saying what number is this term going to? Is it not the series, that individual term? Okay, the sequence number. Okay, big difference between the sequence number and then the series.
So that one does go to 0.
So this one does go to 0 if you did L'Hopital's rule, which doesn't tell us anything, which kind of sucks. If it went to 2, diverge right away. Okay. All right, so that's what they call the direct comparison test. Everybody kind of okay with that? The toughest part about today, at least I think, and you guys get the general concept here, the toughest part of today is picking what your second thing is going to be. What are you going to compare it to? Now, a lot of them are going to be, I think, pretty obvious, but some of them might be a little trickier, so just give them a try. Unfortunately, it might be a little guess and check. And, my advice would be pick ones that you know. Pick ones that you know either converge or diverge real easy. Geometric, P-series, any of those are going to be good to compare to. Okay? All right, let's do another one. This one's called the limit comparison test. And once again, we're kind of comparing that A and B. So we're basically looking at A sub n and B sub n. So we have two different comparisons that we do. Now, sometimes we might run a comparison test, and it might backfire us. We might not be able to see what it's going to work. We might have one that's divergent, and then one that ends up being smaller. That doesn't tell us anything. Okay, so we have to be able to pick the right ones. Now, another way to go about it is what's called the limit comparison test. And let me show you one where you kind of have to do that. Let's do n goes from 1 to infinity, and let's do 1 over 2 to the n minus 1. We want to see if this series converges or diverges. So you can try, at least my advice would be to try the comparison test first. So I try to figure out what you compare that to. So if I took my A sub n, I'd probably pick 2 to the n minus 1. And then what would you probably pick for your B sub n? 1 over 2 to the n, right? 1 over 2 to the n might be one that we know the answer to real easy, right? It's pretty close to it. They're in the same field. So this one right here is going to converge or diverge? Converge. Okay, this one's going to converge because it's a geometric, and the ratio is going to be less than 1. Okay, so geometric is going to converge. Now I just want to see if this guy converges, this guy better be smaller than it. If it's smaller, then we're good to go. Okay. Well, if you look here, the denominator of this one is always going to be smaller than this, which means this number is always going to be bigger. So this guy is going to be bigger. So the direct comparison doesn't tell us anything. Okay. Plus, this 2 to the n would be it'd be really tough to pick a different one to compare it to. This is the correct comparison to pick. Test just doesn't work. Okay. Comparison test doesn't always work. Doesn't always help you. Okay. So this one I would say for now no conclusion. Okay. We're going to get a conclusion, but for now it's a no conclusion. This number's bigger. If it's bigger than something that's converging, that doesn't tell us anything. Okay. All right, so now I want to do what's called the limit comparison test, which says this. It says, well, if I take the limit, as n goes really big, of a sub n over b sub n. If I take the 2 that I picked and I divide them, if that limit right there goes to some constant, some number, it's got to be bigger than 0, unfortunately. It's got to be bigger than 0. If it goes to some number, then that means that both of these converge or both diverge. Okay, so here's, if the limit goes this, or maybe I'll put an if there. If all this stuff works, then both converge or both diverge.
I don't know which one.
Well, you're going to pick one. You're going to pick one that converges, right? Or you're going to pick one that diverges. You can pick 1 over n that's divergent, right?
Go back to it.
But you go back to the original, exactly. Okay. So the limit comparison test says if you take the limit, you go really big, and we've done lots of limit problems. Limit of the original divided by your new term that you're picking right here. If that goes to some constant, some number, then that means that they're both going to be the same. The general idea here, without doing a big formal proof, which the proof of this is actually not too bad, but the idea of this is this. If these two guys are going to converge to about the same level and you divide them, that'll give you some constant number. Okay? If one's going to be way bigger than the other, it might go to infinity. Or if the bottom one's way bigger, then it might go to 0. Okay? So if it goes to 0 or infinity or something like that, then this test fails. We can't really do this test. Okay? If they're about the same level, then they're going to have the same characteristics as far as converging or diverging. So if they're about the same level and it gives us the same level at 2, let's say. If that goes to 2, that means that they're both about the same level. If one converges, the other converges. If one diverges, the other diverges. Okay? So that's the general idea with the limit comparison test. This is how it actually works, though, when you actually do your limit. Okay? So we do the limit as n goes to infinity. And you want to do the original term divided by what you're comparing it to. So we're going to have 1 over 2 to the n minus 1. All that's divided by what we're comparing it to, which is 1 over 2 to the n. Okay, so I'm basically taking these two as my comparisons, putting one over the other. I'm going to run a limit, and I'm going to see what that limit goes to. Gives me a number bigger than 0, jackpot, good to go. Okay, so on this one, I probably won't write it this way too often, just so you know. Instead of dividing, we can just always multiply by its reciprocal, right? So this, I would really just do the limit for this guy as n goes to infinity, and it's going to be 1 over 2 to the n minus 1, and then we're going to multiply that by 2 to the n over 1. Basically the reciprocal of the second one. Okay, so we'll write it in that style. Okay, so now I'm just evaluating the limit of some a sub n formula, a sub n term that we've done before, and I want to see what that goes to. Okay, so if I do this, I'm going to go to the limit as n goes to infinity, and it's going to be 2 to the n over 2 to the n minus 1. And I want to see what this limit's going to go to. So what do you guys think that limit's going to go to? 1. It is going to go to 1. Yes, it is going to go to 1, right? How would you check that? How would you? We kind of skipped a bunch of steps to get here. All right. How would you do that? How would you check this limit? If you plug in infinity, it's infinity over infinity. So L'Hopital's rule. Okay, L'Hopital's rule. So you would take the derivative of this, which is natural log of 2 to the n. Bottom derivative of this is natural log of 2 to the n. Derivative of that is 0. It goes away. So these cancel each other out to 1. So that's why that limit goes to 1. Okay. What's up?
Could you just say that they're both the same power and then?
You can look at that. It's kind of the same idea as that, yes. You could actually divide everything by a 2 to the n is what they want you to do, but that's kind of a lot of overkill, I think. So L'Hopital's rule is kind of nice. All right, cool. So that one goes to 1. Now what that tells me, since that went to a constant bigger than 0, what that tells me is that they both have the same converging, diverging characteristics. So my second one, my b sub n, I know converges. That means that my original one right here has to converge. Okay, so this guy right here converge. Okay? What do you got?
What if it fails?
What if it fails, then the test is inconclusive once again. So you got to find a different way to get there. There's more ways, but for now, for up to now, it's all the stuff that we've done. So you're still looking at geometric, still looking at telescoping, you're still looking at the P-series, you're looking at the asymmetric divergence test. Those are the big ones that we have right now. Okay. All right. So the weird thing about all this, at least I think, is the fact that we ran this limit and it went to 1. And before we did that divergence test that said, well, if it hits 0, we don't know much. But if it hits any other number other than 0, then that tells us it diverges for sure, right? You guys remember that part? So it's a little weird, like the difference between those. Now, the first one that I just said, that was for a specific term to diverge. That's what that divergence test said. So if I just test this for this term diverging, that's that nth term test. Plug in a big number, see if it goes to 0. If it doesn't go to 0, then this part right here has to diverge, okay? If it goes to 0, we don't really know. Could diverge, converge, it's up in the air, okay? There's a difference between that and the comparison limit test. Comparison, I'm actually comparing two different things right here in fraction form, but I'm comparing these two right here to see what it's going to go to, okay? Let's do one more or two more of those to make sure that the limit one's kind of tough to catch on to, I think, at first. So let's do, how about that one? That one's good. So let's do this, and let's call it the square root of n, and then n squared plus 1. I'd like to think this is a little easier than some of those interval tests. Just throwing that out there. All right, so let's compare. I'd probably start with the direct comparison. Just throwing that out there. We might do a limit comparison on this one, but direct comparison would be a good thing to look at, right? What would you probably try to compare that to? If you were to do direct comparison, we're going to do it both ways on this one. But let's do direct comparison. What would you compare that to? What do you think? How about that? It'd be way simple if that 1 weren't there, right? So let's take that 1 off. Right, Daniel? Take that 1 off. I know you're not paying attention. It's not your fault. It's your guess. Okay. So we have a plus 1, right? That's the big difference here. That's the only difference, really. So if we look at this guy, this might be one we could do, right? Now this square root of n over n squared, does that converge or diverge? Be a good thing to think about, right? I don't know. This guy converges. But why? It's a P-series. Yes. It's a P-series, right? Change that to 1 over, right? This would be n to the 3/2, right? Okay, and the 1/2 brings to the bottom or subtract your exponent, either way you want to look at that. Okay, n to the 3/2. Since that power is bigger than 1, that's going to converge. Okay, so this is a converging sequence right here. Now I want to figure out which one's bigger, right? If this one converges and this one's smaller, right, then it has to converge as well, right? So if I take a look at this guy, this one had a plus 1 in the denominator, right? So this guy is going to have a bigger denominator, so this is going to be a smaller term. That means that it's going to go this way like so. That guy has to converge, okay? Now that's the direct comparison way. The limit comparison way would say to do it this way. It would say take the limit as n goes to infinity of the first term, your a sub n, so the square root of n over n squared plus 1. And then we're going to multiply that by the reciprocal of our comparison. Okay, so that's this n to the 3/2 over 1. So n to the 3/2 over 1. And I'll probably always write it in this format right here. It's really a over b, but when you reciprocate it, it's always going to turn into that. Okay. So we're going to simplify this a little bit, run our limit tests on this. So our limit for this, we got n to the 1/2 and then n to the 3/2, that's n squared, right? So n squared over n squared plus 1. And we're just taking the limit as n goes to infinity. Well, as n goes to infinity, the powers are the same there, right? So it's going to be 1 over 1, so this limit's going to go to 1. That goes to a constant that's bigger than 0. That means that these are going to have the same characteristics of converging or diverging. If this one converges, so does this one. Okay? So I showed it a couple different ways, but this one is going to not converge. There's no M in it. All right, so that's the limit comparison. We're going to do one more super harder, tougher one, and then we'll be good for the day. Okay? So general questions? Are we getting the general idea of this at least? Right? It's going to take a couple practice problems in order to maybe have it stick. But. All right, let's do super hard. What's the hardest one I got on this page? Yeah, that one looks nasty. Let's do that one.
Is that n times 2 to the n?
Yep.
Or n squared to the n?
N times 2 to the n. Just take the integral. Do the integral test.
Oh, okay.
Okay, that's what.
Yeah, that'd be gross. Let's not.
Impossible.
We can
That
do it.
sounds like a lot.
I don't want to say nothing's possible.
What do you think? What do you think on this one?
Oh, limit. Well, you can do either.
Limit. Okay.
Can you direct?
What would you compare it
Can't do limit on this.
to? You can't do limit?
Or can't do direct.
So you just
I thought we were
Can't do direct on this one, right? Direct would be a good thing to try at first, at least I think, right? What would you guys probably try to compare that to? N times 2 to the n over 4n to the third, right?
Yeah.
Which we can actually reduce that just a little bit, right? That would be what? 2 to the n, and then divided by 4n squared. You guys are loving the bad math going on. Remember, we're comparing these two. We're not saying they're equal, we're comparing. All right, these two are equal, though. Now, this one, I want to see if this guy converges or diverges. That's kind of gross in itself. How can we check that? Well, let's just see if the a sub n term thing works, right? If I plug in infinity, it's 2 to the infinity over infinity, so that doesn't work. Run L'Hopital's rule on that, right? Well, eventually the bottom is going to go away to a number, but is that ever going to go away when you take the derivative of it? It's just going to continue to be 2 to the n, 2 to the n, 2 to the n, 2 to the n. So this guy is going to win, right? This guy is going to be bigger than the other, so automatically this guy is going to have to diverge, okay? So I know that this term right here diverges. Okay? And I did L'Hopital's rule 3 times in my head to get that. 2 times in my head. 2 times in my head. Okay, so that one diverges. Now I just want to see which one's going to be bigger, right? Well, if I take a look at this one, which one do you guys think is bigger? This one's bigger, right? This one's got to be bigger, okay? This one's bigger because the denominator in this one's bigger, which makes that number smaller, okay? So, so that tells us nothing, okay? That tells us nothing with, if this one diverges, I don't know anything about this one, okay? It's less than it, so it has a chance. It has a chance of either way, okay? So limit comparison is your way to go here on this one. So we're going to, unless you want to take the integral, so we're going to go, the limit is n goes to infinity, and we're going to do n times 2 to the n, and then we're going to divide that by 4n to the third plus 1, and we're going to multiply that by this guy's reciprocal, so we're going to flip that guy over, okay? So it's going to give us a 4n squared over 2 to the n. Now, I could have used this first one, or the second one, it doesn't really matter, they're the same equation, so I don't care which one you use, you'll still get to the same answer, I believe. Okay, so as we simplify this big limit mess, so we get the limit as n goes to infinity. We have some nice canceling going on here. My 2 to the n's cancel. So 4n cubed over 4n cubed plus 1. Limit of that goes to 1. Original divergence. Okay, there we go. Okay.
Only if it goes to a solid amount.
Number, some constant bigger than 0. If that guy goes to infinity, if for some reason it ended up being like, let's say it ended up being like a 4 up here or something like that, right? That would go to infinity, right? So that one we wouldn't be able to tell. Just couldn't do it, okay? We could tell, you actually could. Some calc books go a little bit more involved. Ours doesn't, so we don't have to worry about it too much. Some calc books looked at it. If it goes to infinity, then that actually tells you one thing about one of them, and you can, if you know one of them, then you can kind of guess. But it kind of goes back to a direct comparison after that. So we're not going to do too much of that. Okay. So all right, we're good.
It'll just kind of stay there.
Until right after.
Yeah.